The last type of function in our library of functions is the greatest integer function. This is probably new. You may not have seen this in a previous course. The equation of a greatest integer function is f of x equals, and we use the abbreviation int for integer parentheses x. So when you see that int x, you read this. This is the greatest integer that is less than or equal to x. So you read this notation, int x, the greatest integer less than or equal to x. So before we even look at the graph, let's just practice evaluating this function. So we'll essentially make an xy table. So if I make a table of values here, x and f of x. So if I substitute in, these are just some examples of x values. If I try 1, 2.9, 1/4, and -1/2. So if I want to evaluate f of 1, so f of 1 is going to be int 1. So that's the greatest integer that's less than or equal to 1. Well, with the greatest integer function, if you enter an integer into the function, your answer is just going to be what you put in. So the greatest integer that's less than or equal to 1 is 1. So when you're using the greatest integer function, integers are the easiest things to evaluate. It's just the input is the same as the output. Now, if I want to find f of 2.9, I want to find int 2.9. Oops. I'm going to move this over here. So if I want to find f of 2.9, I want int 2.9. So that means I want the greatest integer that's less than or equal to 2.9. So another way of talking about greatest integer function, if you want that greatest integer less than or equal to it, that essentially means round down on a number line. So if it's an integer, there's no rounding. But if you have a decimal like 2.9, if you plotted 2.9 on a number line and you rounded it down, that would round down to 2. So it's basically like ignoring that decimal portion. So the greatest integer less than or equal to 2.9 is 2. So you're rounding it down to the smallest integer. Okay, then if I wanted f of 1/4, I want int 1/4. I want the greatest integer that's less than or equal to 1/4. Well, 1/4 falls between the integers 0 and 1. I round it down to 0. And then our last example, if I substitute in a -1/2, so if I want int -1/2, the greatest integer that's less than or equal to -1/2. Now be careful on the negative ones. -1/2 falls between -1 and 0. So if I round it down to the smaller one, that would round that down to -1. So you'll have questions in the homework that just ask you to evaluate the function, like they don't even talk about the graph yet. So that kind of takes some practice because this function may be new. Now, when we go to the graph, we can see it's going to be this shape, and that we would describe this as a step function. Because you can see the stair steps. So these are flat steps. So these are constant shapes, constant pieces, but they're diagonally increasing as you go from left to right. The domain, if we put our pencil all the way left here, so here it's starting at -2. You assume this goes all the way to -infinity. You assume this pattern continues all the way to the left. But even if I just start where it's given here, if I go from -2 and I trace from left to right, I've got every x from -2 all the way up. Now here, when I hit an x value of -1, it's not defined, but then it jumps up here to the next step, and it is defined. So here from -1 to 0, I've got a step. But then at 0, it's not defined because that open circle, but it jumps up and here it is. So it ends up covering all the x values. So your domain is -infinity to infinity. Now the range, again, we assume this pattern goes all the way down to -infinity, but if I start at the one on this example drawn here, the y value here is -2. All the points on this step are going to have a y value of -2. Then there's a split. So anywhere between -2 and -1, there's nothing existing here. So it's all the y values here are -2. All the y values here are -1. All the y values in this step are 0. All the y values here are 1. So it's basically skipping anything between the integers. So your range is going to be integers. Just the integers, so no decimal y values. And that's because what this function does is it essentially rounds down, rounds any decimals or fractions down. Now, as far as even and odd, be careful with this. It kind of looks like it has a diagonal increasing, like where if you rotated the paper 180 degrees, you'd have the symmetry. But if you look really closely, each step has a filled-in circle on the left and an open circle on the right. If you were to rotate this 180 degrees, that would swap. So then it would be open circle on the left and closed circle on the right. So it is actually not even or odd. Now, as far as increasing and decreasing, again, although it appears that each of these steps is getting higher as you move left to right, which might suggest increasing, but on each of these steps, they're flat. Those are constant. So as far as increasing and decreasing, we would just say that this is a constant function. It's constant between consecutive integers. So it's constant here between -2 and -1. It's flat, constant here between -1 and 0. It's constant here between 0 and 1, etc. So this is definitely one of the more obscure and unusual functions. It won't come up a whole lot after this section in this course, but there are some nice word problem applications that you'll see in the homework. Specifically, a real-world application of like a cell phone plan is an example of something that could be represented with the greatest integer function.